All right, let's derive the parametrics for the hyperbola. So I'm just looking at one branch of the hyperbola here. There's our random point, xy. And again, I will draw in that circle. X squared plus y squared is equal to a squared. Now the angle, how do we work it out with this one? This is really interesting. We drop a vertical down, but obviously that's not going to hit the circle like it did with the ellipse. But it will hit the x-axis. So at the point that it hits the x-axis, we draw a tangent to the circle, and then that creates an angle at the center. All right? But if you think about it, that angle here, because of geometry, would be the same as the angle between the tangent and the vertical that you've dropped as well. But when we think about it with the auxiliary circle, we think of it, well, it's the angle the radius makes with the tangent when we drop the vertical. And so that's where theta comes into it. So again, it's not simply joining P up to the center and saying that's the angle. That's where the angle is. So what are the coordinates then? Well, the x value, I can use that right angle triangle. X over a will be the secant of theta. So x is equal to a sec theta. The y value, how am I going to get that? I'm simply going to sub it into the known equation of the hyperbola. No, it's not cheating. Okay, so you get a squared sec squared on a squared minus y squared on b squared is 1, and we end up with y is b tan theta when we play around with that. So parametrics for the hyperbola, a sec theta, b tan theta. All right, I'm not going to bother deriving all those like we did with the ellipse. What it turns out to be with the hyperbola, once again, notice it looks very similar to the equation of the hyperbola. When we're dealing with the Cartesian coordinates, we get x1x on a squared minus y1y on b squared equals 1. The normal, instead of getting a squared minus b squared, you get a squared plus b squared. But, of course, that is still equal to a squared e squared. Remember the difference between the ellipse and hyperbola? One was 1 minus e squared, the other was e squared minus 1. So that's why sometimes people prefer to go a squared e squared, because it's the same for both the ellipse and the hyperbola. In parametrics, we get x sec theta on a minus y tan theta on b is equal to 1. And for the normal, the secs and tan are now on the bottom, and the a's and b's are now on the top. A reminder, when we differentiate secant, we haven't really talked about that one, have we? Differentiate sec, you get sec tan. Right, so when you differentiate sec, you get sec tan. Easy enough to prove. If you rewrite sec as 1 over cos, and then differentiate that, you'll see it comes out to be sec tan. Tan, of course, we have seen, that is sec squared when you differentiate it. Okay.